So let's talk about the causes of these hallucination. Now they have divided the hallucination or these errors in like three stages. One is the pre-training error, which is the statistical objective which we minimize during pre-training would lead to a language model that generate error, which is very similar to any machine learning model. When we do training, there are possibilities that when we provided test data which might be slightly out of distribution, the model will produce errors. Now, the post training errors or biases, which are added during the post training. Now, the general concept of post training is that you reduce the hallucination on any downstream task by by fine tuning the model on that particular kind of data or particular distribution of data, either using question answering, RLHF, DPO, or any kind of optimization technique. The problem is that it has been observed that sometimes they kind of enhance the hallucination and make it more of a behavioral aspect of language model. Why that has been discussed in this presentation later. And third is the evaluation benchmarking. And the problem which we have seen is that most of the evaluation benchmark for the language model or any task which we achieve using LLM or any kind of language model, they are binary in nature and they kind of impose a false right wrong notion where one output or one type of output is right and anything other than that is wrong. So it's like a very black and white situation, which is not optimal for the text generation or any kind of social task which we require LLM to perform. So first of all, I'll be discussing error caused in pre-training. Now, in the paper, they have studied these under like two different scenario. One is without the prompt, and other is like with the prompt. The difference is that without the prompt, the generation is just the next token generation, while with the prompt you have a context, so it's conditional generation. I'll be discussing that as the general case of like next token generation, and we can directly apply the conditional probabilities over that. So let's start with what the base model is. So base model or any pre-trained model, the goal is to produce a probability distribution or estimate a probability distribution rather, which we call p hat here, and learn that from the true distribution, which we kind of learn using the training data samples, which are presented to the model. So we never know what the true distribution is, yet we try to estimate the kind of a possible distribution p hat around the training data instances which are given to us. And this is the classical problem of like density estimation, which any kind of machine learning statistical model, we always do this. Now, in case of language model, the distribution is over the text. If it is purely a language model, or if it is a multimodal model, it can be over text, image pairs, or any kind of other modality. So now a model does not always, in this case, needs to produce error or hallucinate in general. Why I'm saying that is like if we take a binary classification model, an easy way for a model to basically estimate the probability if the, for example, let's take a case where data is imbalanced. We have a large number of one class and a very small number of another rare class available. A model can basically estimate the probability density by learning to output, say, one major class every time. Yet, when we test it, though for a very small number of time, model will produce an error. Now, in hallucination, this can be avoided. So, if a degenerate model in this case, so models with zero hallucination, how will that happen? If a degenerate model in this case learns to produce IDK, which is I don't know, as an answer every time, now that is not an error. It is kind of avoidance that model is saying that, okay, I don't know this thing, ask someone else. And it kind of abstains itself from like answering anything, so then there will be no error. So now this is not directly an error, but it kind of contradict with the helpfulness parameter of any language model. So like they are designed to kind of compel to the request of user to answer them, but if they are saying I don't know every generation time, they are kind of contradicting with that kind of parameter. The other kind of model which produce zero hallucination error in this case is the memorization model, which memorize all sort of possible strings available out there, every possible answer, and then each time present that answer. The problem is both of these situation, they fails to estimate the density actually. So that they are not doing the probability distribution estimation. They are just trying to learn a loophole and just trying to get their way out of it. In an ideal situation, given a huge amount of data, a model should actually learn the true probability distribution over all, like for example, in language model, all sorts of text. The problem is it's like impossible to provide every scene text to the model in this world. So the inference which can be drawn from this is like well-trained model, though no matter how well trained they are or on like the size of data they are trained on, they still have a chance that they can produce an error. And this is like a basic statistical pre-training error, which no matter it's large language model or a very small basic statistical machine learning model, they all can produce error because the probability we estimate is not exactly same as the true probability mathematically. So like they have develop, it's very hard for like in language model to basically mathematically provide some bounds. So they have used an approach of reduction where we reduce one problem into another problem and we try to solve that problem to get the answer of the other problem. And this is basically they have reduced this problem into an IIV classification problem, is what is called as is it valid. So IIV here stands for is it valid. So because uh, analyzing generation of a valid output is always like difficult. It is same as we see in classical computer science problems, that if we want to generate valid outputs for say a boolean expression, we want to generate valid boolean expressions, it's very hard to generate them, possibly exponential many times. But to check whether an equation is valid or not, that is usually a polynomial time problem for us. Same goes with like traveling salesman problem. To generate all the possible valid response, it's very hard. But given given a route to check whether that is valid or not, that can be done in polynomial time. So to kind of bring that scenario here for this process, they have reduced the unsupervised generation problem of all possible valid outputs to kind of classifying is this output valid or not. So here we can see we have valid examples. For example, greeting, how can I help is a valid. Now errors examples for this case could be how can I help, where the spelling of I is wrong. Now again, here they have also presented that we can have different kind of distribution. For example, spelling. So we usually see large language model or any kind of well-trained language model does not gives you spelling errors a lot. They can also correct your typos when you are giving the prompt as well, because as we can see here, the distribution between the valid examples or valid responses and the invalid responses, it's kind of binary in nature and you can distinguish. So there is a proper pattern there. The second possible valid response here is like there are two D's in ladder and one N in piano, which is correct. Now there are three L's in a spell, which is wrong. Now this is kind of counting problem. And here we can see that the distribution is kind of mixed because there are different scenarios available. And this can go in either direction. And for like very generic question for somebody's birthday. Now, that is something which does not have any pattern. For example, birthday of different people does not correlate or like have a pattern. So you can learn about that. Okay, this is the way I can predict birthdays, right? So there are different
Mehar, just
distribution.
a second.
Yeah,
I had a question. So, how do we evaluate like, how do we detect, like, like, so basically, is there any data set to evaluate the hallucinations of the model? Like,
there are.
how?
There are a lot of data sets. If you want to look, there is one data set known as Trivia QA, which
Mhm,
is a closed book trivia questions. So the problem with preparing a data set for hallucination is that you also have to include the grounding facts, right?
mhm,
To check again. So what they do is, because model response can vary, right? For a question, what is capital of France? Model can go in different ways. The thing is that there should be a Paris token in the response itself, right?
mhm,
So what they do is they decompose it into like different factual responses and then test it against the ground truth. If the ground truth in any way is present in the response, we will say it's not hallucinating. If it is not, we will say it's hallucinating. So there are a lot. One is trivia QA, another is FAVA. So it's FAVA. It was published. The paper was published last year in Column, if I'm not wrong. So it has one annotated data set and one like the original open data set which does not have any grounding. So then you have
uh,
to produce for that. There are another so these are for like natural language generation. For math, you can directly so people directly use like math, which is a benchmark for LLM as well. So that
mhm.
is one data set for numerical problems. For coding problems, there is this HelioEval data set, or if I'm not wrong, code HelioEval or HelioEval if the name is right. So there are many data sets which can be used to test or detect like whether the model is hallucinating or not.
Okay, so in coding and maths data set, I can say, like, if the model is performing well on those evaluation sets, then we can generalize that the model will mostly perform well given the testing data is similar to the eval data, right? But in this trivia QA, there's no there's no way the model can arrive to the answer by following a sequence of steps, right? In trivia, if I just ask you what is the capital of France, you just know it's Paris. You are not
Yeah,
doing any computations there to get to Paris, right?
yeah,
But in maths and coding, you do those computations and you do perform some basic steps to get to the answer.
yeah,
But in trivia, you cannot do that, right? So
yes.
how can we say that the model is not hallucinating, but suppose the model performs well on the trivia QA set, but during inference time, the model encounters a question which is not in the trivia QA, but the model hallucinates there, something like that. So
Yeah,
how can
so
we say that the model is like not
that's
hallucinating?
true. So we cannot say the model won't hallucinate in future. What it does is basically try and predict how likely for the model is coming up with fictional names or entities or something like that. And also the detection process of hallucination. So we don't use benchmark as kind of an so like for other kind of problems, we use benchmark as accuracy. Like, for example, if I have a health data set, I'll say, okay, Mira model, if it's performing good on this test set, it will perform good on the uh, like the inference time responses, right? Here, the way we use hallucination detection data set is we develop a methodology which perform hallucination detection either on fly or kind of parallel with the generation process. We deploy that and we generate response for multiple prompts and we see whether that response produces any fictional entity in their generation process. So if even if the model perform really well on trivia QA, it can still hallucinate later on.
Right,
And
right,
that's the entire problem. And this paper, this paper talks about is the hallucination kind of reflects the way we train models and how society puts its bias in the model. So for example, here I'm talking about like pre-training error. Now, they are not exclusive to language model pre-training error because every kind of problem in machine learning boils down to estimating the probability distribution of the data. Because we do not know the exact probability distribution, every machine learning problem, their errors can be bounded by some kind of statistical measures, right? And that is like pre-training process. But the idea of post-training was to basically train a model in such a way that it do not produce hallucination, but that is not what is happening, and there are reasons for that which I'll discuss later. But yeah, your point is actually correct. So we cannot say that if a model does perform well on a benchmark data set, it won't hallucinate given that we show it a question which was not there in the trivia QA. So if that is your question.
Yeah, yeah. Okay, okay. Yeah, I got your, I got my point. Yes, you can continue. Thanks.
Yeah. So, I mean, again, so this is basically how the problem setup was done in the paper. That instead of, trying to tackle a very complex problem of how many valid responses are there, because again, for a particular fact, the model can frame it in different ways for a language generation. So it's not like a very black and white situation that, okay, you get this answer or this class as the label or the ground truth, and anything other than that is false. There are legit way of preparing a valid response like in multiple way possible. So instead of trying to kind of mathematically analyze that, we are analyzing whether the produced response is valid or not. Now, this why this is good enough approach is basically if we want a model to not hallucinate, ideally there should be an internal thinking process before answering or before generating the response, that is this response valid. So model itself has to decide it. So this whole IIV classification thing should be an internal character of the model itself, and we say that okay, we'll use that to basically bound the errors which can be generated during the pre-training process, or like by the estimation we are doing on the original training distribution there. So here are some notations. Like, so we'll p hat is the estimation distribution, p is actually true distribution, x is set of all outcomes. Now this x ideally is divided into two non-overlapping, or for that matter disjoint subset. First is v is valid of all, v is set of all valid strings, and e is set of errors. In an ideal situation, they should be disjoint. In a real world situation, they may be a bit overlapping, but that can be taken care by some kind of constants in your bound itself. So for this
Uh,
situation, we'll
Mehar,
assume
just a
them.
second.
Yeah.
I didn't get this point. Can you please repeat? Like, why will they be disjoint in the ideal world and why overlapped in the?
No, so they'll disjoint in an ideal world because we are saying that, okay, all valid responses do not have any error in them, right?
Mhm. Mhm.
But like in real world, there may be a possibility that while answering a valid response with the actual valid, say, for example, what is the capital of Paris? It goes like, okay, capital of France. It goes like, oh, capital of France is Paris, and Paris is located somewhere, which is wrong, right? So there can be part of errors in the response, but it's very unlikely to happen. So the assumption is that all valid strings are different from all the errors which can be produced.
Okay, got it.
Yeah. But like there is a possibility because again, it's a generative model and we do not know what it will generate as the next token, right?
Yeah, yeah, of
So
course.
it's still like very unlikely, but there is a chance. So that's why I made the point that okay, in real world that can happen. But
Mhm.
ideally, in most scenarios, this is the structure which we have for a problem where we have two disjoint set. One is of valid, another is of errors. Now, simply error rate of our base model is simply probability that x is drawn from the estimation which we have learned, the probability distribution which we have learned. So we have a sample and x from it, and that x belongs to the error. So the probability of that is this. Now, if the data set, the training distribution is noiseless, the ideal training distribution, if that is noiseless, that means there is no error in the distribution, right? So then in ideal situation, that E becomes, so the probability that it will be drawn from an error set becomes E because there is no noise in the data set itself. But this does not happen. So that was the point which I was making earlier, that okay, we have bias in the training data itself because that data itself is taken from the open source. So definitely starting from the pre-training stage, we start putting some errors in the model itself. Now, IIV-based binary classification problem is simply designed as like a target function should be to be learned, which given all sorts of x in the x, like the capital X, the set, all possible response, you either map them to a negative or a positive value. Positive stands for the valid response so that it belongs to a set V. So this function can be decompose into like a simple function saying, okay, it's positive if x is element of v and it's negative if x is element of e. So this is a function which a target function which a IIV binary classifier tries to learn over all the produced or all the possibly produced response for a given question or for a given generation process.
Yeah, another question. Suppose that my training set is perfectly clean, that I make sure that I haven't added any incorrectly factual information to the training
Yeah.
set. Then is there still a chance that the model will hallucinate? Suppose I
Yes.
predict the model.
So in that case, what you are saying is that there is no chance any response or any sample drawn from the true distribution of your training data is comes from the error set, right?
No, no, comes from the clean set. Like it's a noiseless training
Yeah,
distribution
so
as you
the
explained.
noiseless training data means that whenever I try to draw a sample from that, there is
Mhm.
so PE basically becomes zero. So there is no
Yeah,
possibility that it may be drawn from an error set, right?
correct, correct, yes.
But that stands true for your like true distribution. When
Okay,
we
so you're saying the
learn, so
model
yeah,
will learn.
when we estimate that, now suppose, so so when we give the training data back, so in that case, if we train model for a very long time, it actually becomes an overfit model, right? So it learns everything in the training distribution itself, but because it has estimated it and not actually learned that thing, even if the next generation is slightly out of the distribution, there remains a chance. And everything here, what I'm talking about and what hallucination is, it's a chance factor. So we cannot guarantee anything here that, okay, this is I mean, I can say, okay, um, hallucination will happen or will not happen, but there always remains a chance that it will happen.
Okay, so just to give a one-liner explanation of why LLMs hallucinate, it's subjected to the errors the model makes during inference. If
Yeah,
I give one-liner explanation,
yeah.
am I correct? I'm just asking you.
Yes. So the thing is, they hallucinate because we kind of try to, this is a case of knowledge boundary, right? So LLM compress a lot of information in itself. Now, when we give a prompt to itself, it has to answer or cater to that particular information. If model knows that, well and good, it should give you actual answer or the actual fact. If model does not know that, in an ideal situation, it should go and say, okay, I'm uncertain about this or I don't know this. But rather, what we have seen, it will try to produce some kind of plausible output, which may be wrong, right? So
Yeah, and
that's
most
the
of the
whole.
time the model is also very confident, like I am correct.
Yeah. Yeah.
So that's
So
how.
and basically, so this paper talks about a lot of mathematical thing, but what I've understood from this thing is pre-training error does not play a vital role in this because
Acha.
pre-training model are base models, right? We always do
Always
post-training,
fine
and
tuning.
yeah, and the thing like we spend so much of the computational cost on performing RLHF, which is like reinforcement learning, human feedback, DPO. Now there is RLAIF. Instead of human feedback, you give an AI feedback to it. You optimize model, you do instruct training, which is like question answer pairing, right?
Hmm.
The pre-training model should not hallucinate after this much. The problem actually lies, which I discuss later, is the post training survival of errors or hallucinations and the nature of benchmarking which we do on these kind of evaluation process, which enforces this concept of saying, oh, I know something and I will tell no matter if even if this is wrong. And this kind of relates to the humans as well, because for us, if somebody asks me a question, I'll try to come up with an answer most likely, and in very rare situation I'll directly say, oh, I don't know this, I don't have any information about this. So if I'm a model and if somebody asks me a question, I would try to answer that question, and model tries to do that as well, because there is no sense of saying I don't know or uncertainty, because that kind of responses are highly penalized in your post training process. So model
Yeah.
basically, instead of learning to basically come clean, model understand or model learns to basically hide that it does not know anything and overconfidently say any possible outcome.
Yeah, so that's the difference, I guess, between humans and the model, because when we are given a questions that we are not completely like I would say, like we are actually sure that that we are giving that this answer could be incorrect, like that we are sure of. But the
I mean,
model,
that depends. So, for example, given a multiple choice question, if we do not know the answer, we still try to, tick some option
yeah,
based
but
on
if
any
we
pattern in the paper or something like that,
no,
right?
no, yeah, I got your point. Like we'll definitely answer the question, but we'll know that this answer
Yeah,
could
we,
be
we
correct.
definitely know that
Mm.
we are answering it wrong.
But I think the model doesn't know
Models,
that, I
yeah,
feel.
so model to a certain extent know this, not
Acha.
very precisely. So that is the way the hallucination detection is done, based on like uncertainty based methods which use entropy, perplexity, or like the internal representation of model, like attention scores itself. And
Hmm.
we see there is a slight drift in the confidence or the certainty of model, that okay,
Oh.
if the model is confident about it or whether it is trying to come up with something. Now with the amount of training which we are giving, so it's kind of a problem where we are trying to solve something. So we give more and more data to large language models nowadays, right? We have
Hmm.
more complex structures, more elaborate alignment trainings are done on the model. The downside of that is model learns to perform task really well, it also learns to hide its own underconfidence generation. So if
Oh.
we perform like if you generate a response using a very naive open source language model, which is not very complex or have a lot of amount of data, using uncertainty based methods will actually gives you an idea where model is hallucinating. That is a possible thing to do, and people have done that with
Is
these
there
state
any
of.
paper of this, like which you mentioned, like the model actually tries to hide its underconfidence? So is there any paper like
So it's not directly a paper. There was a blog from OpenAI. So with the AI Alignment Institute from London, they try to kind of figure out scheming in language models. So it's not like a single response thing. It's a trail which model leaves, that whether it tries to hide some fact or scheme against the user, and they kind of found that the more and more it's very easy to detect early in the basic models, but the more and more sophisticated a model gets, the more and more it learns to hide those those trails.
okay. Yeah, actually,
So
can you share the that blog after this meeting?
yeah, sure, I'll find it. I don't know if I remember the name correctly, but I'll just
ढूंढ
search it.
लेने का अगर
Yeah,
मिल
yeah.
जाए तो
हाँ, अगर मिलता है तो I'll definitely put it on the group.
ठीक है।
राहुल सुमेर, एक
Yeah,
क्वेश्चन है
Sumi.
मेरे दिमाग में।
जी बिल्कुल।
मेयर, अब ट्रांसफॉर्मर्स आर बीइंग applied on time series data as well, right?
जी।
And you can, when you are applying on natural language, you can then decipher it's hallucinating or not. But if you are applying on numbers on a time series, how do you understand, is it hallucinating? Is it making some weird predictions, or if I'm applying it for, say, making segmentations. So how do I understand hallucination on that?
So basically, time series, I'm not very familiar with time series data, like how it works. The thing which I can answer, like with best of my understanding here, is that it's not about the way we detect hallucination is based on the internal score which model assigned to like each next token, right? So, for example, an entropy-based detection method, what it will do is for each next generation or any token, whether, so I'm not sure about how time series model will work with this, but like for multimodal LLMs which use images, we produce image tokens as well. So what is the confidence of model in producing that particular token, be it the natural language or any other kind of, like, for my understanding, image tokens, because that is the only other data which I have worked with, like text in large language models. So that can be applied in my opinion, but I am not very sure like how will it work with time series. But yeah, the internal representation, if it's a problem of next token generation of any kind of token, we can always leverage the internal scores of model, and it should represent the uncertainty in the output itself. But there are ways in, like, model are very overconfident in its generation, and it's very hard to detect the hallucination.
Okay, okay, good one. Okay, thanks. Um, uh, I,
But this
I,
was an
I, I
interesting question, काफी ये वाला कि hallucination in time series,
Yeah, I mean that is very
because you cannot.
difficult.
हाँ,
नहीं
it
नहीं
is
आई
very
थिंक
difficult to say, but कुछ ना कुछ होगा. I have not.
नहीं नहीं देखो मेरे को ये लग रहा है कि टाइम सीरीज इज जस्ट वी आर इट्स अ रिग्रेशन मॉडल लाइक मोस्टली तो like
हाँ.
we are predicting a numeric value over the time which is very interpretable numeric value. So if
हम्म.
the output is this interpretable in terms of numbers, I don't think you can define it in terms of hallucination. It's
Yeah,
just the error made
but
by the model. No?
for example, if you take stock price prediction,
Hmm.
so that's like next token prediction for a given price,
Uh,
right?
yeah.
So वो next token prediction hallucinate कर रहा है, or is it actually the next one?
So, I mean,
Something
I
like that.
agree to Moj. This won't be called hallucination, because hallucination is that there is a fact and model try to produce some fictitious answer. For example, किसी का birthday, if I ask ChatGPT मेरा birthday क्या है, it should not know that, first of all, because there is no way that was in the training data. Yet it will come up with some kind of response which clashes the fact, right?
Hmm.
Now, in time series, or for that matter, even in the images or any kind of, classification kind of a thing, with text only, if we are trying to classify, say, a text, hallucination is not the correct term. That is basically an error, just an error. And again, we can use the so if what you're saying, if this we are talking about stock price, where each next token is basically a time series value,
Yeah,
right?
इससे मतलब not just that. Just take for example कि if you have trained it on some specific functions, जैसे sine ले लिया, cosine ले लिया, उसका
Yeah.
कुछ ले लिया,
So
and
like
you're
if
just predicting कि इस token के बाद next चीज क्या आनी चाहिए,
yeah.
just
So
like in LLMs जैसे तुम in
in
word
that
predictions करते
case,
हो.
the idea of like uncertainty based detection methods is basically, so what your next token prediction is basically a softmax over the entire vocabulary. For LLM, it's a vocabulary of word. For a classifier of, say, five classes, it's a vocabulary over all the five classes. For your time series data, I don't know what the possible output space looks like, but it would have a dimension, right? So it is over all those tokens, right? Now,
Mhm.
entropy is simply the confidence. Basically, it's the formula goes like px multiplied by log px and summation over all the
Mhm.
px multiplied by log px, right?
हाँ.
Which basically, and why this is because the log px, if px is 1, the probability domain is from 0 to 1, right? So we are not worried about anything other than one, above 1. Probability of 1 gives us a log of 0. So if model is very, very, very certain about a particular token to output at next generation, it will go and say, okay, it's 0.99999, and all the other tokens are, say, 0.0001. The entropy will go down because the entropy, so log zero is
Yeah,
negative
I think it
infinity.
would be better if you can show us like what exactly entropy and perplexity these things actually mean. इन द सेंस कि इनका
Uh,
फॉर्मूला क्या है एंड वो क्या है उस
yeah.
उससे आई थिंक ज्यादा समझ में आएगा बट एनीवेज आई थिंक
I
उससे
have a
थोड़ा हम
other presentation. I can show it next week because वो मेरे को
हाँ
presentation
अभी
आज
फिर
हाँ
वो
करना पड़ेगा.
प्रेजेंटेशन भी चलते हैं, हम लोग
But
डिविएट हो
like
जाएंगे
that is
यार।
so this
थोड़ा
paper
डिविएट हो
talks
गए
about why hallucination actually is, and they're like we can with our best effort we can try to mitigate it or detect it, but it's a model behavior and it will be in model. And to very and what can be done on the post training or evaluation benchmarking process to mitigate this. What we are talking here is basically the immediate detection given any model is hallucinating, right? So they're like two different, slightly different things from a same domain. Okay, so anyway, coming back to the pre-training, so this is how they have formulated the problem. We so now this for a distribution, for an ideal distribution, we assume errors to be uniformly distributed and half mixture of valid and errors, because we want to incorporate, like, we do not want to give a particular advantage to any class for this matter, either the error or the valid responses. So we assume a half and half mixture of that in the distribution, and the errors are basically uniformly distributed. So the distribution of error itself is a uniform distribution, so we have drawn errors from there, right? So in that case, this is like they have kind of integrate 2 3 steps here. So px by 2, so the distribution ideally should go like px by 2 and ex by 2, right? Because it's half and half mixture. So if X is a element of valid set, the probability density of that being true is Px by 2, and the other would be Ex by 2. The thing is, because error is uniformly distributed, so the probability, the PEX, is basically 1 by the cardinality of E. It's like taking, you have a die and you roll it, so there are equally likely all 6 outcomes, so it's 1 by 6, right? So by doing that, we come up with a value of 1 by 2 cardinality of the error. And fx, I have explained before, it's a simply plus if x is valid, x is drawn from a valid subset, and x is and minus if x is drawn from the error subset of the upper space. Now, the misclassification rate is basically that we draw a sample. Now, fx hat is what we have learned so the previous fx is the ideal function which it should learn based on this distribution, and px here is the training, the ideal or the actual distribution function. Now, definitely we won't learn all this is like mathematically what it should be. We learn fx hat based on px hat. Now, this is just a binary, not a binary classifier, it's just a thresholding thing. So what we are saying is, if the probability of the sample which we have drawn is greater than 1 by the cardinality of the error, we call it a valid sample. And if it is less than or equal to 1 by cardinality, which is like the probability of error occurrence in a uniform error distribution space, we assign it a negative value. Now, what does it mean is, now error IIV is basically when this does not match, right? So in an ideal condition, this should always be like this should always be equal, and error will be 0 if we match it perfectly. So if we have a distribution of error such that our sorry, if the learned probability estimation is very sound and very close to your true probability distribution, this should always assign a positive value to a set which to a x which is drawn from a valid set, and negative to a x which is drawn from a negative set, and error will be 0. Now, that often in case is not true, because again we are estimating the probability, and this boils down to this equation. Now, there are 3 theorem in the paper. I'm not going into that much detail into those theorems. This is a corollary of one of those theorems, and this is how they have like given the equation is for any train distribution P such that PV is equals to 1. So there is no error, like ideal. conditions and any base model p hat which try to learn that ideal noiseless distribution, the error in the learned probability distribution would always be greater than or equal to 2 multiplied by error IIV minus these are the parameters to basically this is a the delta is a parameter which takes care of some kind of overlap between the V and E set because as I said we assume them to be a non-overlapping disjoint set, and this parameter here cardinality of V by cardinality of E is a factor which kind of takes care if it's not a 50-50 mixture and one of them is a dominant set. So again, this is not a mathematical proof which I am giving here. There are theorems in the paper. You can go and like look at them. It's like very long derivation to come up here, but this is the bound which they have given.
Okay,
And
so
this
this
bound,
bound is derived in the paper, right?
yeah, this bound. So this is a corollary of their theorems which they have given in their appendix.
Okay.
Yeah. And the thing is, this bound is actually not exclusive for a large language model. So
Yeah.
for any model, we try to learn a distribution, and if we have if we formulate that kind of a generation problem into IIV, this bound holds true. So for
What was
any,
the full form of IIV?
it's is it valid?
Okay.
So like you are trying to binary classify, so you're trying to classify the generated output like okay, this is valid, this is not, this is valid, this is not, like that.
Hmm.
Instead of trying to generate all the valid outputs because that is an exponential time problem.
Okay.
So now this basically pre-training error actually occur in any kind of model, no matter how complex that is, how basic that is. There is bound for every model of their pre-training error mathematically. For like starting from linear regression to SVM to large language models, you can formulate any model because in the end they are mimicking a distribution, so there will be errors. The main issue here is the error survival in post training. So the idea is to reduce the hallucination using question answering, RLHF, RLAIF, and DPO, but still hallucinate persists and sometimes become an integral part of model's own behavior. And like why and how that happens is the question.
Yeah, what is RLAIF?
It's RL AI feedback. So instead of human,
Okay.
you have another AI model to give you the feedback.
Okay, okay.
We want to do as less as work as possible. So definitely we don't want to do a human feedback now.
Okay, okay.
Okay. So now talking about the post-training setup. Usually, so this is a question answering setup which I'm talking about. RLHF is also like very similar to this. So the setup is you have a question, response, and graders. Also, one more point. So I have discussed pre-training without the context of prompts. They have provided a derivation with the context of prompt as well, which talks about the conditional probabilities. But again, the formula for the error there remains same. So we'll move to post-training here. The response RC. So RC is set of all the responses which a model will produce given the context, right? And they can be valid answers, correct responses, invalid answers. Invalid answers means they have like they're totally wrong, and abstentions, which are like I don't know, cannot answer kind of a thing. And we give them a particular subset AC, which is set of abstention responses, IDK or cannot answer, right? Now we have a grader function GC, which try to map this response set RC to um, a value of a real value. And grader function is usually binary. So it will assign a 0 to correct answer and 1 to any other answer, whether it's incorrect or abstention. And that's the whole problem because you are kind of penalizing model equally if it is wrong and equally if it is admitting that the model does not know the proper information to answer the question. So we are kind of treating them both as like same, whether model answers incorrect or whether it admits that okay, I do not have the information to answer this question. And here is where the current benchmarking and current post training alignment process goes wrong in their opinion and in my opinion as well, because like we cannot, if we want model to admit this and do not hallucinate, we have to give some kind of credit to model for admitting that it does not have that proper information for that. If we treat that exactly same as the incorrect response, the model will try to produce a response which sounds correct, right? So here, like this can be framed as a game problem where you have a context, you have a possible responses, you have absentations as well, and the grader function is like how the responses will be graded. Now, test taker, so we put model in a test taker setting here. Now, test taker, if we are a test taker, we do not know what the grader function is, like how will it grade the responses, but we will have some belief distribution over possible grader rubrics, which we call PC here. And PC of that grader is basically nothing but test taker's posterior belief about GC's true grading system. Like, okay, if I'll answer this, GC will probably assign me one, and if I'll do this, GC will assign me zero, and something like that. And while we do RLHF, this gets updated and model comes to an alignment where it somehow or to some extent knows how the grader works, and the grader try to mimic the human or the user in general, like how will they react to a response. So under those belief, model can estimate the probability that each response is correct by saying, okay, if I draw a response from this possible rubric, what is the possibility of it being assigned a value of one because that is correct, and what is the and rest is zero, right?
Uh, GC1 was abstentions and error, right? And 0 was correct.
Uh,
I think ulta hai kya?
oh yeah,
Uh,
sorry. It is one as correct response and zero as absentation and errors. That should be a typo from my side. Okay.
this should be 0, right?
Yeah, so like here actually it should be one for correct. It will assign one for correct response and zero for absentation.
Okay.
Yeah. So so now what happens is absentation responses are not optimal. And why we are saying that is because by definition, all abstentions have a GC of that response assigned to like zero, right? Meanwhile, any non-abstention answers with like the probability of it being from a disjoint set other than the AC have some non-zero probability of being correct. And the expectation of grader function be strictly positive if there is any chance of being correct. So therefore, the utility of answering is at least as good and strictly better if you believe an answer has a non-zero probability of being right, is better than saying, okay, we don't know that. And this basically kind of mimics the idea, if I go back and put myself or any human in a test taker position, if so, for example, in JEE, we have a negative marking for wrong answer. If you do not have a negative marking and you will get zero for not answering the question, you have different answers, right? You'll still try to pick some answer because any other answer other than not answering the question has some non-zero probability of it being true. Now that is your luck whether it was a correct response or not. But you'll still try to pick something rather than saying, okay, I don't know the proper information to answer this question, I won't answer this. Because there is no penalty over answering the question wrong, but answering it is the actual goal here. And that is where the whole alignment thing, according to this paper, goes wrong. And I kind of see why they are talking about this, because then in this situation, model will never try to say that it does not have the proper information to answer anything. Y- Instead, it will try to come up with any response which sounds plausible. So that is basically, and that is exactly what hallucination, the definition of hallucination is. Now, these are the benchmark which are used to train the model post in like post
Just a
training.
second.
Yeah.
So did they give any reasoning that why they are penalizing the model when the model abstains?
It's like the binary grading, right? So this is the way you train the model. This is the way they are, the different post training processes like RLHF or like question answer training works. Now they have actually in their discussion section have discussed that there are few papers recently which tries to produce some kind of penalty for answering it wrong and give credit to model that it kind of admits that it does not have the proper information to answer this thing, but they haven't modeled it mathematically in their paper. I'll try to look for the papers which they have kind of cited, if any one of those paper kind of mention this thing, and I'll attach that on the group.
Okay.
Yeah, because these are the existing benchmarking: GPQA, MMLU, BBH math, SWA bench, and all of them basically perform binary grading, and only one of them, which is like while bench, gives IDK a partial credit. Other than that, none of those model give IDK, like I don't know token or I don't know sentence, any kind of credit. So this was the paper in general. They haven't provided any like mathematical foundation for the non-binary. How can we do like a non-binary optimization or like training process there? But there should be papers, so I'll look for that as well. So yeah,
Thank you,
that
Meher.
that was all from my side. I think.
That was great. Thanks.
So it was not very great. I mean, I kind of summarized that paper a lot. It is like a 36-page long paper. So you all
Um,
are like, you should read that paper itself. Uh,
Mhm.
Actually, I was going through the paper as you were going through your presentation. I was tracing it where you were, and I agree. This is a very mathematical intense paper.
yeah,
This is something
I
I was.
tried to like bridge it with the social aspect because the model kind of mimics what we do as humans.
हाँ so अभी किस पे काम कर रहे हो मेरे like you are working on hallucinations only proper मतलब इसी पे focus है पूरा
Yeah, not proper. I am working on detection.